In this demonstration, you'll learn how to set up a modal structural simulation to study the results of vibrations and mode shapes of a circular plate. I'll start by selecting a simulation process template from the study panel on the left here. I'm going to select the structural template. I'll leave the default physics type of structural only. I can either do a static structural analysis or a modal analysis. In this example, I'll select a modal analysis and accept the default selection for the options list. Typically, automatic contact detection is also performed. In creating my simulation process, the first thing that I'm asked to do is select a geometry. I'll select the design model or geometry file for this simple circular plate, a very common geometry used to demonstrate modal analysis. AIM loads the geometry and sets up a simulation process which will define everything I need to do for a modal analysis. While this is not a particularly time-consuming process, it is not interesting to view, so I'll skip ahead. The geometry is now loaded. AIM has automatically created the physics solution process, which involves the geometry input, meshing, physics, and results. Here is a summary of all of the tasks created along with their status. These tasks are also shown in the workflow window in the data flow diagram format. The first thing we need to do is add a support, which we do in the physics solution task. I'll click on physics in the workflow view to go into the physics solution task. You'll see that a lot of defaults have already been set for me: material assignments, physics options, and solver options. If we take a look at the default solver settings for this analysis, we can see that we are requesting 6 eigenvalues by default. Now, I'm going to add a fixed support to the 2 faces of the plate, which makes the plate fully clamped at the ends. I'll first use the face selection filter to select the faces on the side of the plate. Then, I'll add the support boundary condition from the context menu. The boundary condition should now be up to date, and my physics solution is all set up. I'll solve this physics solution now. Because the meshing task was also ready to update, it will be automatically updated first. Once the meshing task is updated, AIM will move on to update the physics solution task. I can see the progress on the bottom right-hand side here. This simulation is now solved, so we can look at the resulting eigenvalues here on the output of the physics solution panel. You can see that we have the 6 modes generated by default. Now I can view my results. I want to add the modes and animate them. First, I add a displacement magnitude, and I want the results for mode 1. Then I can evaluate to view the mode shape for this mode. Right-click and I can animate the displacement for this mode. I can view the animated displacement results for all of the modes. This concludes this demonstration of an end-to-end basic modal structural analysis in AIM.